10 gemstones with the most bizarre origins. Some gemstones are born in fire, others are formed in complete geological silence. One took shape inside the hollowed structure of a dinosaur's fossilized bone. Another was forged from Earth's surface as it melted during a meteor strike, then cooled mid-air before falling back as glass. Beneath the floor of an ancient ocean, the shell of a long-extinct marine creature hardened over millions of years into an iridescent gemstone. These origins are not the stuff of myth. They are tangible, studied, and measurable, documented by geologists, paleontologists, and planetary scientists. From fossilized forests to fragments of destroyed protoplanets, each of the gemstones in this list begins not with polish or cut, but with a story so improbable it defies ordinary understanding. This is not just a collection of beautiful stones. This is a record of catastrophe, transformation, and survival, told through the only witnesses that remain. Don't forget to press and hold that like button, leave a comment, and hit subscribe before we begin. Ranked 10th. Jet, fossilized wood from a Jurassic forest. The cliffs of Whitby, on England's northeastern coast, reveal more than sediment and shale. Embedded within the strata lies a material shaped not by magma or tectonics, but by pressure and time alone. Jet. Unlike most gemstones, jet has no crystalline structure. It forms when pieces of driftwood, primarily from Araucariaceae trees, are buried under layers of fine sediment during the Jurassic period. Over millions of years, the wood undergoes a process of anaerobic fossilization. Water is expelled. Volatile compounds disappear. What remains is a compact form of lignite, a carbon-rich, jet-black substance capable of a mirror-like polish. The term jet itself originates from the French word jaillet, derived from the ancient Greek gagates, which is named after the Ganges River in modern-day India, where similar material was once collected. But the most significant historical jet deposits lie in the alum shale beds of Yorkshire. These coastal seams, dated to be over 180 million years old, preserved not only petrified wood, but also an entire cultural legacy that had been layered over geological time. Archaeological discoveries confirm the use of jet in ornamentation as early as the Neolithic period. It appears in Bronze Age burial sites across Britain and Iberia, carved into beads and amulets. Its deep black surface, capable of a soft yet durable finish, made it desirable across cultures. But it was in 19th century Britain that jet reached its social and economic peak. After the death of Prince Albert in 1861, Queen Victoria adopted jet jewelry as part of her mourning attire. This act transformed the fossilized wood into an emblem of bereavement, prompting widespread demand throughout Europe and North America for jet rings, brooches, and carved cameos. During this time, the town of Whitby supported over 200 workshops dedicated solely to jet carving. What sets jet apart from other ornamental materials is not rarity alone, nor age. It is the transformation itself. Few gemstones trace a lineage that begins as living matter. Fewer still carry no crystalline identity, no metallic sheen, and no internal fire. Yet jet endures, silent, organic, geological. Its value lies not in brilliance, but in its past. A stone that remembers the forest from which it came, and the centuries of human hands that carved it into a symbol of mourning. Ranked 9th. Amber, the fossil that preserved a world. Long before it hardened, amber flowed. Originating as tree resin from prehistoric conifers, particularly species of the family Ceatopidiaceae and Araucariaceae, amber began as a viscous, golden substance exuded from bark wounds. In its earliest form, it served a biological purpose, protecting the tree from infection and insects. But once released, the resin followed gravity, dripping to the forest floor, catching leaves, spores, and occasionally, life. In rare cases, insects, spiders, and even small vertebrates became trapped in the sticky substance. Those moments of entrapment, frozen in mid-motion, are now preserved with astonishing detail. Over tens of millions of years under burial in the absence of oxygen, the resin fossilized. Molecular polymers are bonded. The substance matured. What was once soft and scented became chemically stable and optically transparent, transforming into amber. Geological evidence indicates that the majority of high-grade amber deposits are between 30 and 90 million years old. The most famous comes from the Baltic region, particularly around Kaliningrad and Lithuania, where vast fossilized resin beds are still mined today. Other significant sources include the Dominican Republic, Myanmar, formerly Burma, and parts of Mexico. Each deposit has its geochemical fingerprint. For example, Baltic amber is rich in succinic acid, a compound once believed to have therapeutic properties, hence the commercial term succinite. Amber's significance extends beyond geology. It is one of the earliest ornamental substances used by humans. Beads made of amber have been found in Upper Paleolithic burials dating back over 13,000 years. In the Bronze Age, trade routes formed around the extraction and distribution of amber, particularly through Central Europe's Amber Road. The material was valued not only for its warmth and glow, but also for what it captured, an unbroken glimpse into long-extinct ecosystems. In the scientific world, amber holds extraordinary importance. Paleobiologists have studied fossilized insects within it to reconstruct prehistoric food webs, evolutionary pathways, and even the spread of ancient diseases. These are not imprints or casts. They are three-dimensional biological specimens preserved at cellular resolution. Amber's origin defies gemstone convention. It is neither mineral nor crystal, and yet it holds more information than most stones ever could. Its value is not measured in brilliance, but in memory, sealed within layers of hardened resin, untouched for millions of years. Ranked 8th, petrified wood jasper. When forests became stone. In select regions of the world, the past is not buried, it is fossilized in color. Petrified wood jasper is not a gemstone formed in the traditional sense. It is the physical result of trees that did not decay. Under specific geological conditions, when volcanic ash or mineral-rich floodwaters covered ancient forests, the environment sometimes became anoxic, lacking oxygen. Under such circumstances, bacteria failed to break down the organic material. Instead, dissolved silica began to seep into the cellular structure of the tree, atom by atom, over thousands of years. This form of permineralization replaced the tree's lignin and cellulose with cryptocrystalline quartz. However, unlike pure silica or colorless chalcedony, the resulting stone often displays a kaleidoscope of iron oxides, manganese, copper, and carbon, all introduced by variations in groundwater. What once was bark, ring, and fiber now survives as vibrant patterns of red, brown, cream, gold, and black. In the right specimen, the wood structure remains so intact that growth rings, knots, and even insect burrows can still be identified. The most famous deposits are located in the southwestern United States, particularly in Arizona's Petrified Forest National Park, where entire prehistoric log beds, dated to the late Triassic period, over 200 million years ago, remain preserved across a barren plain. Similar occurrences have been documented in Indonesia, Madagascar, and Argentina, each with its geochemical signature. The variety from Arizona tends to show bright iron-stained reds, while Indonesian material often reveals deeper tones of honey, ochre, and dark caramel. Petrified wood jasper underwent complete molecular substitution. Nothing of the original organic material remains, yet the stone retains the external and internal architecture of the tree with astonishing fidelity. It is a paradox of preservation, a fossil that is no longer itself, yet perfectly shaped by what it once was. Collectors, geologists, and lapidary artists prize this material not for its rarity, but for the clarity of its transition. Among all fossil-based gemstones, few demonstrate the complete transformation from living matter to geological artifact as completely, or as visually, as petrified wood jasper. Ranked 7th, dinosaur bone agate. Fossilized bone turned to gem. When vertebrate paleontology meets mineralogy, the result can be unexpectedly beautiful. Dinosaur bone agate is not a gemstone in the traditional crystalline sense. It is the product of fossilization taken one step further, when the porous structure of ancient dinosaur bones, often over 100 million years old, becomes infiltrated by silica-rich groundwater. As the organic material decays and disappears, Microscopic channels and marrow cavities are gradually filled with chalcedony, quartz, or opaline silica. The process is precise and extremely rare. Not every fossilized bone becomes agatized. It requires a delicate balance of pH levels, mineral saturation, and time. What emerges is a dense, gem-quality stone that preserves the internal lattice of the original bone down to its vascular canals and cellular architecture. Under magnification, some specimens reveal hexagonal or web-like patterns unique to specific dinosaur species. These stones are typically found in the Morrison Formation of the western United States, particularly in Utah, Colorado, and New Mexico, where late Jurassic sedimentary layers yield both vertebrate fossils and favorable conditions for silicification. Other known deposits occur in parts of China and Mongolia, although these are less frequently of lapidary-grade quality. Dinosaur bone agate preserves actual anatomical structure in crystalline form. The result is not an accidental visual, but a precise record of prehistoric biology rendered in semi-translucent quartz. Coloration varies depending on the trace elements involved. Iron oxide introduces red or brown tones, manganese may produce black or purple, and carbon can lead to deep grays. Despite its dramatic name, no viable DNA remains within these stones. Their scientific value lies not in genetics, but in structure. While paleontologists use unaltered fossils to study morphology, the agatized variants serve a different purpose, linking paleobiology to gemology and reminding collectors that Earth's oldest skeletons did not always fade to dust. Some became stone. Some of that stone is beautiful enough to be cut, polished, and preserved for display. Each slice of dinosaur bone agate is a cross-section through deep time, an object that is simultaneously biological, geological, and artistic. In the world of gemstones, very few can claim a lineage that once walked the earth. Ranked 6th, Ammolite, gemstone of a vanished ocean. Roughly 70 million years ago, the shallow seas that once covered what is now Alberta, Canada, teemed with shelled marine creatures called ammonites. These cephalopods, extinct relatives of modern squids and nautiluses, possess tightly coiled shells composed primarily of aragonite, a crystalline form of calcium carbonate. Over time, some of these shells underwent a unique form of fossilization, distinct from simple mineral replacement, a process in which a mineral replaces the original material. Instead of turning to stone, a thin outer layer of aragonite survived and became iridescent under specific geological conditions. The result is ammolite, a rare biogenic gemstone composed almost entirely of fossilized ammonite shell. It forms within the Bearpaw Formation, a marine sedimentary layer dating back to the late Cretaceous period. Ammolite's shimmering surface, which displays full-spectrum color play, is derived from the microstructure of aragonite platelets arranged in precise wave-like patterns. Light diffracts through these layers, producing optical interference similar to that seen in opal or butterfly wings. Yet this effect in ammolite originates not from hydrated silica, but from fossilized biological architecture. Commercially viable ammolite is found almost exclusively along the eastern slopes of the Rocky Mountains in Alberta. The material is so geologically constrained that its origin can often be traced within a few kilometers. Mining is conducted primarily by hand, and because the aragonite layers are fragile and thin, sometimes less than a millimeter thick, most specimens must be stabilized with backing material for use in jewelry. Ammolite was formally recognized as a gemstone by the World Jewelry Confederation in 1981. Despite its relatively recent entry into the gem trade, it has gained popularity in both Western and East Asian markets. In some traditions, particularly in feng shui, ammolite is regarded as an energy stone, though such claims lie outside scientific validation. What distinguishes ammolite from other fossil-based gemstones is its surface. It does not merely preserve biological form, it refracts light through biological function. A record of an extinct organism's protective armor has become an object of ornament and trade, not by accident, but through a chain of precise geochemical events that preserve color, texture, and luster across tens of millions of years. Among gemstones formed from ancient life, ammolite remains one of the few that continues to reflect the brilliance of the ocean from which it came, layered, fractured, and fossilized in light. Ranked fifth, Tektite, the glass created by impact. When a meteor strikes Earth at hypersonic speed, the event leaves more than a crater. In rare cases, it leaves a glass-like residue. Tektite is a natural glass formed during the most violent geological collisions, such as meteorite impacts that are powerful enough to liquefy terrestrial rock. Upon impact, the surface material is instantaneously melted by temperatures exceeding 2,000 degrees Celsius and then ejected into the atmosphere. As it cools while falling back to Earth, the molten debris solidifies into aerodynamic shapes, spheres, droplets, or flattened buttons, resulting in a glassy material with no crystalline structure. Tektites are formed entirely from surface materials, not the meteorite itself, but the Earth it struck. Their composition includes silica, aluminum, iron, and trace elements that vary depending on the regional geology of the impact site. The defining feature of tektite is its morphology, characterized by pitted surfaces, flow lines, and splash forms that preserve the dynamics of re-entry. Many specimens contain no water at all, an indication of their rapid, high-heat formation and lack of crystallization. Tektites are found in geographically distinct strewn fields, regions where debris was scattered following significant impacts. The four recognized fields are the Australasian, by far the largest, dating approximately 790,000 years ago, Central European, Ivory Coast, and North American. Within these, various local names have emerged. Moldavite in the Czech Republic, for instance, is a green variant associated with the Reese impact structure. Indochinite, found across Southeast Asia, presents in jet black, deeply etched forms. Georgiaite and Bediacite from the United States are rarer and have an olive tone. The age of tektites can be measured with precision using radiometric dating, linking them directly to known impact craters. In the case of Indochinites, the likely source is a long-eroded crater in Southeast Asia. Despite being thousands of kilometers from the suspected impact site, the material was launched into the upper atmosphere and dispersed over an immense area, an atmospheric scattering event on a planetary scale. Tektites do not contain fossils, nor do internal Earth processes form them. Their existence is a geological exception, the product of extreme pressure, explosive heat, and extraterrestrial velocity. In the context of gemstones, their origin is neither mineralogical nor organic, but ballistic. They are objects shaped by chaos, cooled by gravity, and recovered from silence. Ranked fourth, Moldavite, the gemstone forged in an impact cloud. Green in color, glassy in texture, and found only in a small region of Central Europe, Moldavite is chemically and structurally linked to a single event, the Reese impact. This asteroid collision occurred approximately 15 million years ago in what is now southern Germany. The impact vaporized part of the Earth's surface, ejecting molten terrestrial material into the upper atmosphere. Some of that material cooled and solidified while airborne, eventually falling across what is now the Czech Republic, southern Bohemia, and parts of Austria. The result, a field of naturally formed silica glass, uniquely green, now known as Moldavite. Moldavite displays a translucent olive to bottle green hue, caused by its higher content of iron and manganese. Its structure remains amorphous, lacking any internal crystal lattice, and its surface in unpolished form shows deep etching, grooves, and fluted patterns. These surface textures are not decorative. They are records of chemical weathering and ablation during atmospheric flight. Geochemically, Moldavite contains between 75% and 80% silicon dioxide, with varying traces of aluminum, potassium, and other elements. It is non-hydrated, brittle, and often filled with Le Chatelierite inclusions, fossilized bubbles of pure silica formed under sudden extreme heat. What makes Moldavite particularly unusual is not just its extraterrestrial connection, but also its precise origin. All gem-grade Moldavite can be traced to a singular geologic event, the formation of the Reese crater. Its strewn field is tightly mapped. Its chemical signature is consistent. No other green tektite exists in such quality, abundance, and traceability. The stone's known deposits are dwindling. Most commercial Moldavite originates from South Bohemia, specifically near the towns of Chlum and Besedness, where open pit mining has now been restricted. Because it is not replenishable and formed under unique planetary conditions, Moldavite is considered finite not just in volume, but in origin. It does not come from magma. It does not come from life. It comes from an instant of cosmic force. Terrestrial matter turned airborne, cooled in the sky, and returned to Earth as green glass. Of all stones linked to meteor impacts, Moldavite remains the only one widely used in jewelry whose origin is both extraterrestrial in cause and unmistakably terrestrial in material. Ranked third, Lapis Lazuli, the stone that outlived empires. In the northeast of Afghanistan, in the Koksha Valley of Badakhshan province, a vein of deep blue metamorphic rock has been mined continuously for over 7,000 years. This rock, known as Lapis Lazuli, is not a mineral but a composite, primarily composed of lazurite, with calcite, pyrite, and trace minerals intergrown within a single matrix. Its blue hue, ranging from denim to ultramarine, is not uniform. It is the product of geologic complexity and regional pressure metamorphism. The formation of lapis lazuli is not fully replicated anywhere else on Earth at the same level of intensity or purity. It occurs in contact metamorphic zones, where limestone or dolomite layers were intruded by igneous material. The heat and chemical exchange from this intrusion caused the host rock to recrystallize, resulting in the formation of lazurite, a rare silicate mineral that contains sulfur. Its physical composition is unremarkable by gemological standards: opaque, moderately soft, Mohs 5 to 5.5, and prone to fracture. Yet its role in human civilization exceeds that of most transparent gemstones. In Mesopotamia, lapis was carved into seals and inlaid into burial goods. In ancient Egypt, it appeared in royal jewelry, sacred amulets, and cosmetic pigments. The stone's pigment, ground into a powder, became the source of ultramarine, the most expensive blue used by Renaissance painters, reserved for depictions of the Virgin Mary and royal subjects. Trade routes developed around lapis lazuli long before the advent of silk, gold, or spices. By the Bronze Age, fragments from the Afghan mines had reached as far west as the Iberian Peninsula and as far east as the Indus Valley. Its appeal was not based on brilliance, hardness, or optical effects, but on its scarcity and cultural weight. Geologists consider its formation unusual due to the precise thermal and chemical conditions required for lazurite to occur in large concentrations. The world's highest quality specimens still come from Sarisang, a site that has been mined for millennia using hand tools and vertical shafts cut directly into the cliffside. Lapis lazuli owes its mystique not to a single catastrophic event or exotic composition, but to cultural persistence. It has passed through the hands of artisans, priests, emperors, and merchants. And yet the mine from which it came, harsh, remote, and geopolitically unstable, has changed remarkably little. Its origin is not bizarre because of what formed it, but because of what endured. Ranked second, Peridot in Pallasite meteorites. Gemstones from planetary boundaries. In certain meteorites, the boundary between rock and metal is not theoretical, it is visible. Pallasite meteorites, a rare class of stony iron meteorites, preserve this transition with extraordinary clarity. An interlocking structure of iron-nickel alloy in gem-quality olivine crystals. When cut and polished, these meteorites reveal semi-transparent green stones suspended in a metallic matrix. The olivine, when sufficiently clear and well-formed, is classified gemologically as peridot. Meteoritic peridot crystallized under entirely different conditions, inside differentiated planetesimals. These were early protoplanetary bodies, large enough to have developed cores, mantles, and crusts before being disrupted by collisions. The pallasites that reach Earth are believed to have originated from the core-mantle boundary of such a body, destroyed during the early chaotic era of planetary formation. Only a small number of pallasite falls have been recorded, with peridot large and transparent enough to be faceted. Among the most significant is the Esquel meteorite, discovered in Argentina in 1951. Whose polished cross-sections display peridot gems embedded in a metallic lattice with exceptional clarity. Others, such as the Brenham, USA, and Fukang, China meteorites, have also yielded peridot-bearing specimens, though typically in smaller or more fractured crystals. These peridotites are chemically identical to those found on Earth, magnesium iron silicates. But their formation history places them among the oldest solid materials in the solar system, with radiometric ages exceeding 4.5 billion years. Unlike most gemstones, which form on a single planet under known conditions, these crystals record cooling events, metallic differentiation, and impact fracturing in environments that are no longer accessible for study. In the context of gemology, meteoritic peridot remains virtually absent from the commercial market. Most specimens are kept in scientific collections or museum archives due to their rarity and significance. When cut for display, they are not sold as jewelry, but exhibited as structural remnants of planetary interiors. Among all known gemstones, only a few originate outside Earth. Fewer still can be traced to a vanished planetary core. Peridot and Pallasite meteorites occupies that narrow intersection between geology and astrophysics, a crystalline fragment of something that never finished becoming a world. In first place, Zircon, the oldest solid thing on Earth. Long before continents formed, before oxygen filled the atmosphere, and before the moon even existed, zircon had already crystallized. Zircon is a common accessory mineral found in igneous and metamorphic rocks, but certain grains discovered in the Jack Hills region of Western Australia have revealed something exceptional, ages exceeding 4.4 billion years. These tiny crystals, no larger than grains of sand, are the oldest known terrestrial solids. Their formation predates Earth's oldest rocks and rivals the estimated age of the moon's formation. What makes zircon scientifically invaluable is its ability to incorporate trace amounts of uranium into its crystal lattice while excluding lead. Over time, uranium decays into lead at a predictable rate, allowing precise radiometric dating. This geochemical integrity, combined with zircon's resistance to heat, pressure, and erosion, turns each grain into a geological archive. Some zircons have survived multiple cycles of crust formation and destruction, while preserving isotopic evidence of liquid water, continental crust, and even potential microbial activity on the early Earth. Zircon forms deep underground, crystallizing from silicate melts under high temperatures. Its physical appearance varies from colorless to golden brown, blue, or even red, depending on the presence of trace elements and radiation exposure. Gem-quality zircon has been used ornamentally for centuries, though it is often confused with synthetic cubic zirconia, a different, unrelated material. Genuine zircon possesses high double refraction and intense fire, yet these optical traits are not what place it atop this list. Among all gemstones, only zircon can serve simultaneously as a mineral, an artifact, and a witness. A single grain may record a chapter of Earth's history that no longer exists in rock. It is not the product of biological decay, impact trauma, or ocean sediment. It is a survivor formed during the infancy of the planet, untouched by mass extinction, ice ages, or erosion. A substance that has endured conditions no longer present on Earth, yet continues to exist in laboratory slides, museum drawers, and mountain cores. Zircon is not rare in volume, nor luminous in comparison. Its value lies in what it cannot forget. In the vast record of gemstones, only one holds the memory of a world that hadn't yet begun. Gemstones are often seen as objects of value, cut, weighed, traded, and worn. But value can come from more than color, clarity, or carat. It can come from the origin. Each stone in this list carries not only beauty, but also a record of its past. A record of impact, of pressure, of silence, of extinction. These are not symbols. They are remnants of ancient forests, shattered planets, vanished oceans, and biological forms that no longer exist. Their value lies in what they remember. And yet these 10 are only the beginning. Because while most gemstones form in predictable ways, a few are linked to something else entirely. Belief, fear, protection. Let us know which one resonates with you in the comments, and don't forget to like and subscribe to our channel for more content like this.